We're doing a deep dive today into a really specialized piece of technology. The mission is simple: to get you up to speed fast on how modern distribution networks are, well, ditching the complexity of old copper cables. I mean, we're talking about a massive logistics headache. The core problem this thing solves is running lots of different TV and satellite signals over really, really long distances.
Exactly. Think of a huge stadium or a college campus where the main dish is maybe miles from where people are actually watching TV.
Right, and you can't just use normal coaxial cable for that.
You can't. So what this system does is it takes three independent RF or radio frequency inputs,
Okay, what kind of inputs?
specifically two satellite L-band signals, and then, a regular terrestrial off-air TV signal. It bundles all three of them together to run over a single strand of optical fiber.
So you're basically turning those electrical signals into light.
We're moving them onto light. And what's really interesting is that the L-band signal itself is already an intermediate frequency. Is what comes out of the satellite dish L and B after it's been stepped down.
So let's just unpack the immediate physical benefit here. You're replacing what, like a trunk of 5, maybe 9 bulky copper cables.
At least. And you're swapping all of that for just one single piece of glass fiber.
That simplification alone is huge. But does it also solve the distance problem? You know, with copper, you constantly need repeaters.
It absolutely does. And this is the real game changer. This system can distribute signals to, I think, up to 32 different receivers.
32. And how far away can they be?
Within a 10-kilometer radius, that's a little over 6 miles. With copper, you'd need powered, expensive repeater stations every kilometer or so. This just wipes that whole headache off the table.
Okay, that is a massive shift in infrastructure planning. But I have to ask, if you have 3 separate signals traveling down one tiny strand of glass, how do they not just crash into each other? How do you keep them from interfering?
Right, that's where the technical magic comes in.
I was hoping you'd say that.
It's a technology called coarse wavelength division multiplexing, or CWDM for short. Think of it like a prism, but in reverse. The transmitter has a built-in multiplexer that uses a few different lasers. Each signal gets its own unique color of light, its own wavelength.
Ah, so they're like cars in different lanes on a highway.
Exactly. They all travel together down the same fiber, but because they're different colors, they don't interfere. Then the receiver at the other end separates them back out.
That's a fantastic way to put it. Now, fiber is incredibly clean, but you have to handle it right. So what kind of quality control is built in to make sure those light pulses stay perfect?
Good question. The system has built-in automatic gain control, or AGC.
EGC.
It basically acts like an automatic volume control, stabilizing the output so the signal is always at a consistent, safe level.
And what about the physical connections? Those must be critical.
They are. The system uses what are called SPAPC connectors. The APC stands for angled physical contact.
Angled. Why angled?
Because that angle polish completely eliminates reflections right at the connection point. Reflections in an optical line are like static or an echo on a phone line. It creates noise. The angle just kills it.
Got it. Okay, so connecting this back to the big picture, you said this is an ideal solution for a 1 by 32 multi-dwelling unit.
Yes, an MDU, a large apartment complex, for instance.
So 32 points sounds like a lot, but how does that translate into the number of people, the actual subscribers?
Well, that's the crucial part. Those 32 are just the primary receiving points. At each of those points, the light is converted back to RF and then fed into local multi-switches.
Ah, so each of the 32 points can then branch out even more.
Exactly. Each of those points can create its own local distribution system for dozens of homes or outlets. So while you start with one fiber, the total number of subscribers being served, it can easily be over 1,000.
Wow. Over 1,000 homes from a single fiber optic line.
That's how you get massive economical distribution.
So the major takeaway for you here is that huge signal distribution isn't about fighting electrical resistance in bulky copper anymore. It's about turning that whole complex burden into these neat, efficiently managed beams of light.
And that actually brings up a really interesting question for you to think about. Considering this system needs high optical power and very precise wavelengths to work over 10 kilometers, and then you're splitting that light 32 ways, what do you think the biggest technical challenge becomes, besides just the distance? Is it managing the tiny cumulative power loss across every single one of those optical splitters? Or is it making sure the lasers that create those precise colors stay perfectly stable, even in different temperatures?